I don't see the little thing saying it is recording. Oh, there it is. Okay. All right, so we ended up last lesson talking about exponential functions, how to represent exponential functions. How do you recognize, if you're given a table of value, what should you recognize in particular your output values to kind of give you a clue that you're dealing with an exponential function? What should you see? A constant ratio, absolutely. And what does that constant ratio represent in your exponential equation? So when we divide it and b, the base raised to the x power, excellent. Let me ask you this. If b is greater than 1, is that growth or decay? It is growth. And so for it to be exponential decay, that base has to be a proper fraction between 0 and 1. So what we're doing today is we're just talking about different types of applications. Like, why are we learning? We did talk last week about a real world example. The growth of like bacteria or the spread of a disease at the initial stages kind of represents exponential growth. So even though we said it wasn't really in the long-term exponential growth, let's go ahead and look at some other applications. So on this first one, so we're in the notes. Well, let's take a look at where we can see an example of exponential growth or decay with respect to a population and with respect to money, because, you know, everybody wants to grow their money. Yeah, nodding heads. So if you invest, let's say with respect to money, let's say we invest money into an account and our investment is compounded. Okay, so let's talk about what that means. So here is the formula for compounding interest at a discrete number of times during the year. So if I were to look at this formula, this A of t is some amount that we have at some time t. So this A of t is telling us how much money, what amount of money do I have at some time t. So A, the amount of money we have, is a function of t. Now, let's look at all the variables in this formula and make sure that we understand them. Now, P kind of resembles our A in our exponential function that we've worked with so far. P, let me put that in purple. P is your principal. That is your initial amount when t equals 0. So when t equals 0, I'm at my initial amount. P is my initial amount. And that kind of makes sense because if we look at that parentheses raised to some n times t, if t is 0, the exponent is 0. And as so long as that base is not 0, that equals 1, which yields p. Now, what is R in this formula? R is the rate, that percentage, and we write it written as a decimal. So the rate that we're increasing in this case, hopefully, money. N is the number of compoundings per year. Like, how often am I calculating the interest? So some examples of N. Well, I could compound my money annually. If I'm compounding it annually, what does that imply? How many times a year? 1. If it's semi-annually, how many times per year? 2. If it's quarterly, how many times per year? 4. And monthly? And daily? 365. So if your word problem says I am compounding monthly, you know n equals 12 in the formula. So you have to read the word problem to see what you are substituting in for the values of the variables. Now t is time. So t is just time of years or in years. Okay. So if I want to know how much money I will have after 10 years, T would be 10. And then again, A is what we said was that accumulated amount. That was a function of time. Now, if n equals 1, if I'm compounding annually, let's look at this formula and let's see what happens when n is 1. So if n equals 1 and I substitute into the formula, I have A of t equals p times 1 plus r over n when n is 1 is just r, times n equals 1 times t is just t. So normally if you're compounding annually, where n equals 1, the formula reduces to that. And the formula will change depending on how many times per year you compound your interest. So that's nice. We now understand what this formula represents. Let's see how to use it. Now, in this case, I'm not talking about money. I'm just talking about a population that could be growing or decaying. We could be increasing the number of people, or we could be decreasing. A city population, which was initially 15,500. So what does that number represent in our formula? P. So P is 15,500, has been dropping 3%, has been dropping 3%. So is our population increasing or decreasing? It is decreasing, and if I want to write 3% as a decimal, what would it be? 0.03. Excellent. Now, if we want to write an exponential function and graph the function and use the graph to predict when the population will drop below 8,000, let's think about how I'm going to write that equation. So A of t, the amount of people I have in my population at some time t, is, we said our initial amount was 15,500, and that is 1, right, from our formula up here, 1 minus 0.03 to the t power. Now, why did I let n equals 1? Because I'm dropping 3% every year, a year. It's dropping, so I'm compounding per year. So that's how I can let n equal 1. Does everybody see that? We okay with this formula? Well, I want to simplify what's in that parentheses. So let's go ahead and do that. I still have my initial population. And then if I have 1 minus 0.03, what does that give me? Monday morning at 8:07. Can we do the subtraction? 0.97. Thank you, Jeffrey. Now, is this going to be growth or decay based on my formula? And is it decay? Yes, it is, right? So this is a proper fraction. That's a number less than 1 but greater than 0. So I do know that it is decaying, and it should be decaying. So that's a beautiful formula. And now it's saying, when will the population drop below 8,000? So how am I going to figure that out? Thank you. How am I going to figure out when the population drops below 8,000? What do I do with this formula? Where does that 8,000 go? At A of t. So I'm going to take this A of t and I'm going to set it equal to 8,000. So I really want the population to be less than that, but let's see when it equals that. We have a calculator. If I were to put that function into the y equals, well, what would I have to do? Let's put this equation into the calculator, and what am I looking for in the table of values? If I put this function into my calculator, so y equals 15,500 times 0.97 to the, and we can say x, we can let our input equal x if you want. Where am I looking in the calculator? Do we need to do this together? on the calculator? Do you need to see this? Okay, let's do this together. We're putting this function into the calculator. Finding where the y value is below 8,000. That's fantastic. That is absolutely perfect. You are absolutely correct. Did everybody hear that? I'm desperately trying to open up my, there we go. Heaven help me. Go ahead and see if you can figure out how to answer the next question. What will the population be in 300 years? Y equals, let me get rid of this. Let me get rid of this. Let me get rid of this. And I'm going back up. And I'm putting 15,500 times 0.97 raised to the x. And I'm looking for when y is 800. My calculator is very slow this morning on the computer. Did we figure out what value of x would cause our y to be 8,000? Okay, between 21 and 22 years then, right? Oh, heavens. There we go. So we go below 8,000 right here. So between 21 and 22 years, right, is when, okay, let me quit the screen. Heavens. Let me go back here and share here. All right. I don't know if y'all saw that. Did you see that? Was that up there? I can't tell if it was projecting or not. So between 21 and 22 years, population will drop below 8,000 people. Because it's a word problem, so we're answering in a complete sentence. Now, what will the population be in 300 years? What information have I given you? What variable does that represent? T. So all I have to do is come back in here and figure out what A of 300 is. And what did you get? Oops. 1. Yeah, 1 person. Approximately, yeah, 1.6. You have to round down, right? Because you can't have a fractional part of a person. So approximately 1 person will be left in 300 years. Heaven help us. All right, that's compounding at discrete points in time, right? After a certain length of time each year. Well, what happens if I want to compound continuously? What does that mean and how do I do it? So I'm not saying every other day. I'm not saying every week, every month, every day even. What if it's continuously, like every breathing moment, you are compounding your interest? Well, this is a wonderful use of that lovely natural base E. So this is commonly referred to as the Pert formula. So you compound continuously. If you see the word continuously, you need to think of that natural base E. So here's that formula. P is still the principal, R is the rate, T is the time, but we now introduce that base. So is this growth or decay? If we remember what E is, right? It's growth, yes. Now, When she was born, Mary's parents deposited $10,000 into an account. What does that $10,000 represent? Our principal, our initial amount, P. An account that pays 7% interest. Oh, what does that represent? Rate. And as a decimal, that would be what? 0.07. And it's compounded continuously. So that implies E. Now, after 18 years, Mary withdraws all the money and starts paying for college. How much money does she have to put towards her college? Well, let's write our equation. So A of T equals P times E to the RT. Let's fill in what we know. P, we said, was 10,000. We have E, R is 0.07, and then that's times T. So if I want to know how much money she has after 18 years, what does that 18 represent in our formula? Time T, right? So I want A of 18. So I just substitute in 18 for T. And what do you get? Tell me. How much money does Mary have? How much? $35,254.21. So how many digits do I need to see? Well, this is money, so I better see my dollars and my cents, right? Units of measure, I need to see the dollar sign. I need to see I have a complete sentence. Now, suppose you, we okay with that? Okay. Suppose you have $12,000 to invest. So now my principal is $12,000. We want to know where to invest it. Do I want option A or do I want option B? Well, if I'm investing my money for 3 years, T equals 3, here's my principal. Do I go with option A where my rate is 7% compounded monthly, meaning N is what? 12. Or do I go where I invest my money with a 6.85% as a decimal? What would that be? 0.0685, but it is compounded continuously, which means I'm using my little Pert formula, right? You tell me, where would you put your money? Where are you going to get more after 3 years? And tell me how much you would have after 3 years. Let's write each of those equations, and you tell me where would you put your money. So you try to do it. I'll do it in the meantime. So hopefully you're using each of these formulas to answer those questions, or the question. So if I'm looking for after 3 years, I'm letting T equal 3. Being ever so careful to put this in the calculator with the appropriate notation so it can use the order of operations correctly. Does anybody have their answer? You think you got it wrong? Well, I don't know. We're going to talk about the amounts and then talk about how to get them if we're stuck. You decide where you would put your money, A or B. Don't say it out loud. You can check. Ruby, did you check with Maddie? Did you get the same answers? Parker, Cullen, did y'all agree? No. Boy, where are you going to put your money? Talia, do you know? You don't know where you're putting your money yet? Anybody know where they're putting their money? Well, Maddie's putting it in A. Parker, are you just agreeing with Maddie or do you really think it's A? What did you get? How much money you have after 3 years if you invest in A? And 11 cents. Don't you want your cents? Yes, this is correct. Option A, this is how much you have after 3 years. Who got this? Okay, if we didn't get it, Emma, can we get it? Jeffrey? Yes? Clara? All right. Yes, Ruby. 14,000 what? I get something a little bit different. 14,737 and give me my cents. You think you're going to go to the bank and they're going to, I mean, what would you do if they say, you know what, we just going to round up. We're just going to round down. We're not giving you the cents. You're going to say, I want my cents, because if you're compounding, that cents gets compounded too, right? All right, so by substituting into each of these equations, where would you make the most money? Obviously now. A. Oh, that's hideous. A. So you would invest in A. So let's go ahead and say that 7% compounded monthly yields a better return. And then by how much? By a difference of what? How much more would you make? $57.44. Oh my goodness gracious. I can think of a lot to buy with that. A couple of math erasers, rulers, Tinker's calculator. Right? So, I mean, we need to be able to answer that question. So you better believe when you're going to the bank and they're like, do you want to invest in a CD that pays 3%? And do you want to invest in this? You got to know where to put your money if you want to optimize and get the largest return on your investment, ROI. These are all business things. You should care about this. Yes? Okay, so compounded a certain number of times a year, we use the first formula. Compounded continuously, as soon as you hear the word continuously, you use PERT. You use the base E. Okay? Any questions on this? No questions. Okay, I'm going to return to you. Is there any questions on this? Now would be the time to ask. So actually go ahead and forget them. Any questions on this? Yes? And then it's just automatically contributes to the Xbox. Does that make sense? Any questions? Was this condos or quiz or that's it. Everybody get there? Yeah. Any questions on this? Speak now or forever hold your peace. Do we understand how to do all of those? Yes? Yes. Oh my goodness gracious. I'm coming. Put everything else away. All you need is a pencil. I told you every day. Wait,